A radioisotope thermoelectric generator is an electrical generator that uses an array of thermocouples to convert the heat released by the decay of a suitable radioactive material into electricity by the Seebeck effect. RTGs have been used as power sources in satellites, space probes and unmanned remote facilities such as a series of lighthouses built by the former Soviet Union inside the Arctic Circle. RTGs are usually the most desirable power source for robotic or unmaintained situations that need a few hundred watts of power for durations too long for fuel cells, batteries, or generators to provide economically and in places where solar cells are not practical. Safe use of RTGs requires containment of the radioisotopes long after the productive life of the unit. History. In the same brief letter where he introduced the communications satellite, Arthur C. Clarke suggested that, with respect to spacecraft, the operating period might be indefinitely prolonged by the use of thermocouples. RTGs were developed in the U.S. during the late 1950s by Mound Laboratories in Miamisburg, Ohio under contract with the United States Atomic Energy Commission. The project was led by Dr. Bertram C. Blank. The first RTG launched into space by the United States was SNAP-3 in 1961, aboard the Navy Transit 4A spacecraft. One of the first terrestrial uses of RTGs was in 1966 by the U.S. Navy at uninhabited Fairway Rock in Alaska. RTGs were used at that site until 1995. A common RTG application is spacecraft power supply. Systems for nuclear auxiliary power units were used for probes that travel far from the Sun, rendering solar panels impractical. As such, they were used with Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Galileo, Ulysses, Cassini, New Horizons and the Mars Science Laboratory. RTGs were used to power the two Viking landers and for the scientific experiments left on the Moon by the crews of Apollo 12 through 17. Because the Apollo 13 moon landing was aborted, its RTG rests in the South Pacific Ocean, in the vicinity of the Tonga Trench. RTGs were also used for the Nimbus, Transit and LES satellites. By comparison, only a few space vehicles have been launched using full-fledged nuclear reactors, the Soviet Rossat series and the American SNAP-10A. In addition to spacecraft, the Soviet Union constructed many unmanned lighthouses and navigation beacons powered by RTGs. Powered by strontium-90, they are very reliable and provide a steady source of power. Critics argue that they could cause environmental and security problems as leakage or theft of the radioactive material could pass unnoticed for years, particularly as the locations of some of these lighthouses are no longer known due to poor record keeping. In one instance, the radioactive compartments were opened by a thief. In another case, 3 woodsmen in Georgia came across 2 ceramic RTG heat sources that had been stripped of their shielding. 2 of the 3 were later hospitalized with severe radiation burns after carrying the sources on their backs. The units were eventually recovered and isolated. There are approximately 1,000 such RTGs in Russia. All of them have long exhausted their 10-year engineered lifespans. They are likely no longer functional, and may be in need of dismantling. Some of them have become the prey of metal hunters, who strip the RTGS metal casings, regardless of the risk of radioactive contamination. The United States Air Force uses RTGs to power remote sensing stations for TOP-ROCC and Seebeck radar systems predominantly located in Alaska. In the past, small plutonium cells were used in implanted heart pacemakers to ensure a very long battery life. As of 2004, about 90 were still in use. Design. The design of an RTG is simple by the standards of nuclear technology. The main component is a sturdy container of a radioactive material. Thermocouples are placed in the walls of the container, with the outer end of each thermocouple connected to a heat sink. Radioactive decay of the fuel produces heat which flows through the thermocouples to the heat sink, generating electricity in the process. A thermocouple is a thermoelectric device that converts thermal energy directly into electrical energy using the Seebeck effect. It is made of 2 kinds of metal that can both conduct electricity. They are connected to each other in a closed loop. If the 2 junctions are at different temperatures, An electric current will flow in the loop. Fuels. Criteria. The radioactive material used in RTGs must have several characteristics. It should produce high-energy radiation. Energy release per decay is proportional to power production per mole. Alpha decays in general release about 10 times as much energy as the beta decay of strontium-90 or cesium-137. Radiation must be of a type easily absorbed and transformed into thermal radiation, preferably alpha radiation. Beta radiation can emit considerable gamma X-ray radiation through Bremsstrahlung secondary radiation production and therefore requires heavy shielding. Isotopes must not produce significant amounts of gamma, neutron radiation or penetrating radiation in general through other decay modes or decay chain products. Its half-life must be long enough so that it will release energy at a relatively constant rate for a reasonable amount of time. The amount of energy released per time of a given quantity is inversely proportional to half-life. An isotope with twice the half-life and the same energy per decay will release power at half the rate per mole. Typical half-lives for radioisotopes used in RTGs are therefore several decades, although isotopes with shorter half-lives could be used for specialized applications. For spaceflight use, the fuel must produce a large amount of power per mass and volume. Density and weight are not as important for terrestrial use, unless there are size restrictions. The decay energy can be calculated if the energy of radioactive radiation or the mass loss before and after radioactive decay is known. Selection of isotopes. The first two criteria limit the number of possible fuels to fewer than 30 atomic isotopes within the entire table of nuclides. Plutonium-238, curium-244 and strontium-90 are the most often cited candidate isotopes, but other isotopes such as polonium-210, promethium-147, cesium-137, cerium-144, ruthenium-106, cobalt-60, curium-242, americium-241 and thulium isotopes have also been studied. 238 Pu, 90 steradians, plutonium-238 has the lowest shielding requirements and longest half-life. Its power output is 0.54 kilowatts per kilogram. Only 3 candidate isotopes meet the last criterion and need less than 25 ohm of lead shielding to block the radiation. 238 Pu needs less than 2.5 ohm, and in many cases, no shielding is needed in a 238 Pu RTG, as the casing itself is adequate. 238 Pu has become the most widely used fuel for RTGs, in the form of plutonium-4 oxide. 238 Pu has a half-life of 87.7 years, reasonable power density, and exceptionally low gamma and neutron radiation levels. Strontium-90 also requires little shielding, as it decays by I-squared emission, with negligible I-cubed emission. While its half-life of 28.8 years is much shorter than that of 238 Pu, it also has a much lower decay energy. Thus its power density is only 0.46 kilowatts per kilogram. Because the energy output is lower, it reaches lower temperatures than 238 Pu, which results in lower RTG efficiency. 90 steradians is a high-yield waste product of nuclear fission and is available in large quantities at a low price. 210 Pu, some prototype RTGs, first built in 1958 by the U.S. Atomic Energy Commission, have used polonium-210. This isotope provides phenomenal power density because of its high radioactive activity, but has limited use because of its very short half-life of 138 days. A kilogram of pure 210 Pu in the form of a cube would be about 48 ohm monoxide and emit about 140 a kilowatt, 242 centimeters, 244 centimeters, 241 am. Curium-242 and curium-244 have also been studied as well, but require heavy shielding for gamma and neutron radiation produced from spontaneous fission. Americium-241 is a potential candidate isotope with a longer half-life than 238 Pu. 241 am has a half-life of 432 years and could hypothetically power a device for centuries. However, the power density of 241 am is only 1/4 that of 238 Pu, and 241 Am produces more penetrating radiation through decay chain products than 238 Pu and needs about 18 ohm of lead shielding. Even so, its shielding requirements in an RTG are the second lowest of all possible isotopes, only 238 Pu requires less. With a current global shortage of 238 Pu, a closer look is being given to 241 Am lifespan. Most RTGs use 238 Pu, which decays with a half-life of 87.7 years. RTGs using this material will therefore diminish in power output by a factor of 1 or 0.51/87.74, or 0.787%, per year. 23 years after production, such an RTG will have decreased in power by 16.6%, that is providing 83.4% of its initial output. Thus, with a starting capacity of 470 AW, after 23 years it would have a capacity of 392 AW. However, the bimetallic thermocouples used to convert thermal energy into electrical energy degrade as well. At the beginning of 2001, the power generated by the Voyager RTGs had dropped to 315 AW for Voyager 1 and to 319 AW for Voyager 2. Therefore in early 2001, the RTGs were working at about 67% of their original capacity instead of the expected 83.4%. This lifespan was of particular importance during the Galileo mission. Originally intended to launch in 1986, it was delayed by the Space Shuttle Challenger accident. Because of this unforeseen event, the probe had to sit in storage for 4 years before launching in 1989. Subsequently, its RTGs had decayed somewhat, necessitating replanning the power budget for the mission. Efficiency: RTGs use thermoelectric couples or thermocouples to convert heat from the radioactive material into electricity. Thermocouples, though very reliable and long-lasting, are very inefficient. Efficiencies above 10% have never been achieved and most RTGs have efficiencies between 3 and 7%. Thermoelectric materials in space missions to date have included silicon-germanium alloys, lead telluride and tellurides of antimony, germanium and silver. Studies have been done on improving efficiency by using other technologies to generate electricity from heat. Achieving higher efficiency would mean less radioactive fuel is needed to produce the same amount of power, and therefore a lighter overall weight for the generator. This is a critically important factor in spaceflight launch cost considerations. A thermionic converter an energy conversion device which relies on the principle of thermionic emission can achieve efficiencies between 10 and 20%, but requires higher temperatures than those at which standard RTGs run. Some prototype 210Po RTGs have used thermionics, and potentially other extremely radioactive isotopes could also provide power by this means, but short half-lives make these unfeasible. Several space-bound nuclear reactors have used thermionics, but nuclear reactors are usually too heavy to use on most space probes. Thermophotovoltaic cells work by the same principles as a photovoltaic cell, except that they convert infrared light emitted by a hot surface rather than visible light into electricity. Thermophotovoltaic cells have an efficiency slightly higher than thermocouples and can be overlaid on top of thermocouples, potentially doubling efficiency. Systems with radioisotope generators simulated by electric heaters have demonstrated efficiencies of 20%, but have not been tested with actual radioisotopes. Some theoretical thermophotovoltaic cell designs have efficiencies up to 30%, but these have yet to be built or confirmed. Thermophotovoltaic cells and silicon thermocouples degrade faster than thermocouples, especially in the presence of ionizing radiation. Dynamic generators can provide power at more than 4 times the conversion efficiency of RTGs. NASA and DOE have been developing a next-generation radioisotope-fueled power source called the Stirling radioisotope generator that uses free-piston Stirling engines coupled to linear alternators to convert heat to electricity. SG prototypes demonstrated an average efficiency of 23%. Greater efficiency can be achieved by increasing the temperature ratio between the hot and cold ends of the generator. The use of non-contacting moving parts, non-degrading flexural bearings, and a lubrication-free and hermetically sealed environment have, in test units, demonstrated no appreciable degradation over years of operation. Experimental results demonstrate that an SRG could continue running for decades without maintenance. Vibration can be eliminated as a concern by implementation of dynamic balancing or use of dual opposed piston movement. Potential applications of a Stirling radioisotope power system include exploration and science missions to deep space, Mars, and the Moon. The increased efficiency of the SRG may be demonstrated by a theoretical comparison of thermodynamic properties, as follows. These calculations are simplified and do not account for the decay of thermal power input due to the long half-life of the radioisotopes used in these generators. The assumptions for this analysis include that both systems are operating at steady state under the conditions observed in experimental procedures. Both generators can be simplified to heat engines to be able to compare their current efficiencies to their corresponding Carnot efficiencies. The system is assumed to be the components, apart from the heat source and heat sink. The thermal efficiency, denoted ITH, is given by where primes denote the time derivative from a general form of the first law of thermodynamics, in rate form. Assuming the system is operating at steady state and ITH, then, can be calculated to be 110 a W/2000 a W equals 5.5%. Additionally, the second law efficiency, denoted I2, is given by where ITH, Rev is the Carnot efficiency, given by in which the sink is the external temperature and 363 K for the SRG, and the source is the temperature of the RTG, assumed 823 K. This yields a second law efficiency of 14.46% for the RTG. Safety. Radioactive contamination. RTGs pose a risk of radioactive contamination. If the container holding the fuel leaks, the radioactive material may contaminate the environment. For spacecraft, the main concern is that if an accident were to occur during launch or a subsequent passage of a spacecraft close to Earth, harmful material could be released into the atmosphere. Therefore their use in spacecraft and elsewhere has attracted controversy. However, this event is not considered likely with current RTG cask designs. For instance, the environmental impact study for the Cassini-Huygens probe launched in 1997 estimated the probability of contamination accidents at various stages in the mission. The probability of an accident occurring which caused radioactive release from one or more of its 3 RTGs during the first 3.5 minutes following launch was estimated at 1 in 1,400. The chances of a release later in the ascent into orbit were 1 in 476. After that, the likelihood of an accidental release fell off sharply to less than 1 in a million. If an accident which had the potential to cause contamination occurred during the launch phases, the probability of contamination actually being caused by the RTGs was estimated at about 1 in 10. In any event, the launch was successful and Cassini-Huygens reached Saturn. The plutonium-238 used in these RTGs has a half-life of 87.74 years, in contrast to the 24,110-year half-life of plutonium-239 used in nuclear weapons and reactors. A consequence of the shorter half-life is that plutonium-238 is about 275 times more radioactive than plutonium-239 per gram compared to 0.063 curies/g. For instance, 3.6 kg of plutonium-238 undergoes the same number of radioactive decays per second as 1 ton of plutonium-239. Since the morbidity of the two isotopes in terms of absorbed radioactivity is almost exactly the same, plutonium-238 is around 275 times more toxic by weight than plutonium-239. The alpha radiation emitted by either isotope will not penetrate the skin, but it can irradiate internal organs if plutonium is inhaled or ingested. Particularly at risk is the skeleton, the surface of which is likely to absorb the isotope, and the liver, where the isotope will collect and become concentrated. There have been several known accidents involving RTG-powered spacecraft. The first one was a launch failure on April 21, 1964, in which the U.S. Transit 5BN-3 navigation satellite failed to achieve orbit and burnt up on re-entry north of Madagascar. The 17,000 Asai plutonium metal fuel in its SNAP-9 RTG was injected into the atmosphere over the southern hemisphere where it burnt up, and traces of plutonium-238 were detected in the area a few months later. The second was the Nimbus B-1 weather satellite, whose launch vehicle was deliberately destroyed shortly after launch on May 21, 1968 because of erratic trajectory. Launched from the Vandenberg Air Force Base, its SNAP-19 RTG containing relatively inert plutonium dioxide was recovered intact from the seabed in the Santa Barbara Channel 5 months later, and no environmental contamination was detected. In 1969, the launch of the first Lunokhod lunar rover mission failed, spreading polonium-210 over a large area of Russia. The failure of the Apollo 13 mission in April 1970 meant that the lunar module re-entered the atmosphere carrying an RTG and burnt up over Fiji. It carried a SNAP-27 RTG containing 44,500 Asai of plutonium dioxide, which survived re-entry into the Earth's atmosphere intact, as it was designed to do, the trajectory being arranged so that it would plunge into 9 kilometers of water in the Tonga Trench in the Pacific Ocean. The absence of plutonium-238 contamination in atmospheric and seawater sampling confirmed the assumption that the cask is intact on the seabed. The cask is expected to contain the fuel for at least 10 half-lives. The U.S. Department of Energy has conducted seawater tests and determined that the graphite casing, which was designed to withstand re-entry, is stable and no release of plutonium should occur. Subsequent investigations have found no increase in the natural background radiation in the area. The Apollo 13 accident represents an extreme scenario because of the high re-entry velocities of the craft returning from lunar space. This accident has served to validate the design of later generation RTGs as highly safe. To minimize the risk of the radioactive material being released, the fuel is stored in individual modular units with their own heat shielding. They are surrounded by a layer of iridium metal and encased in high-strength graphite blocks. These two materials are corrosion and heat resistant. Surrounding the graphite blocks is an aeroshell, designed to protect the entire assembly against the heat of re-entering the Earth's atmosphere. The plutonium fuel is also stored in a ceramic form that is heat resistant, minimizing the risk of vaporization and aerosolization. The ceramic is also highly insoluble. The most recent accident involving a spacecraft RTG was the failure of the Russian Mars 96 probe launch on November 16, 1996. The two RTGs on board carried in total 200 Ag of plutonium and are assumed to have survived re-entry as they were designed to do. They are thought to now lie somewhere in a northeast-southwest running oval 320 km long by 80 km wide, which is centered 32 km east of Iquique, Chile. Many beta MRTGs produced by the Soviet Union to power lighthouses and beacons have become orphaned sources of radiation. Several of these units have been illegally dismantled for scrap metal, fallen into the ocean, or have defective shielding due to poor design or physical damage. The U.S. Department of Defense Cooperative Threat Reduction Program has expressed concern that material from the beta MRTGs can be used by terrorists to construct a dirty bomb. 28 U.S. space missions have safely flown radioisotope energy sources since 1961. Nuclear fission, RTGs and nuclear power reactors use very different nuclear reactions. Nuclear power reactors use controlled nuclear fission. When an atom of U-235 or Pu-239 fuel fissions, neutrons are released that trigger additional fissions in a chain reaction at a rate that can be controlled with neutron absorbers. This is an advantage in that power can be varied with demand or shut off entirely for maintenance. It is also a disadvantage in that care is needed to avoid uncontrolled operation at dangerously high power levels. Chain reactions do not occur in RTGs, so heat is produced at an unchangeable, though steadily decreasing rate that depends only on the amount of fuel isotope and its half-life. An accidental power excursion is impossible. However, if a launch or re-entry accident occurs and the fuel is dispersed, the combined power output of the now radionuclides set free does not drop. In an RTG, heat generation cannot be varied with demand or shut off when not needed. Therefore, auxiliary power supplies may be needed to meet peak demand, and adequate cooling must be provided at all times including the pre-launch and early flight phases of a space mission. Subcritical multiplicator RTG, because of the shortage of plutonium-238, a new kind of RTG assisted by subcritical reactions has been proposed. In this kind of RTG, the alpha decay from the radioisotope is also used in alpha-neutron reactions with a suitable element such as beryllium. This way a long-lived neutron source is produced. Because the system is working with a criticality close to but less than 1, that is Kef less than 1, a subcritical multiplication is achieved which increases the neutron background and produces energy from fission reactions. Although the number of fissions produced in the RTG is very small, because each fission reaction releases almost 30 times more energy than each alpha decay, up to a 10% energy gain is attainable, which translates into a reduction of the 238 Pu needed per mission. A subcritical multiplicator RTG was investigated at the Idaho National Laboratory at the Center for Space Nuclear Research in 2013. RTG for interstellar probes. RTG have been proposed for use on realistic interstellar precursor missions and interstellar probes. An example of this is the innovative Interstellar Explorer proposal from NASA. An RTG using 241 was proposed for this type of mission in 2002. This could support mission extensions up to 1,000 years on the interstellar probe, because the power output would be more stable in the long term than plutonium. Other isotopes for RTG were also examined in the study, looking at traits such as watt per gram, half-life, and decay products. An interstellar probe proposal from 1999 suggested using 3 advanced radioisotope power source. The RTG electricity can be used for powering scientific instruments and communication to Earth on the probes. One mission proposed using the electricity to power ion engines, calling this method radioisotope electric propulsion. Models: a typical RTG is powered by radioactive decay and features electricity from thermoelectric conversion, but for the sake of knowledge, some systems with some variations on that concept are included here. Space: the ASG is not really a RTG, it uses a Stirling power device that runs on radioisotope. The BES-5 bike reactor was a fast breeder reactor which used thermocouples based on semiconductors to convert heat directly into electricity. The SNAP-10A used enriched uranium fuel, zirconium hydride as a moderator, liquid sodium-potassium alloy coolant, and was activated or deactivated with beryllium reflectors. Reactor heat fed a thermoelectric conversion system for electrical production. Terrestrial, nuclear power systems in space, known spacecraft nuclear power systems and their fate. Systems face a variety of fates, for example, Apollo's SNAP-27 were left on the Moon. Some other spacecraft also have small radioisotope heaters, for example each of the Mars exploration rovers have a 1-watt radioisotope heater. Spacecraft use different amounts of material. For example, MSL Curiosity has 4.8 kg of plutonium-238 dioxide, while the Cassini spacecraft has 32.7 kg. See also. References. Notes. External links: NASA Radioisotope Power Systems website, a RTG page, NASA JPL briefing, Expanding Frontiers with Radioisotope Power Systems, a gives RTG information and a link to a longer presentation, Space Views, the Cassini RTG debate, Stirling Radioisotope Generator, DOE Contributions, a good links, Idaho National Laboratory, a producer of RTGs, Idaho National Laboratory MMRTG page with photo-based virtual tour.